My name is Hyun-Sebu, and I'm gonna give you a presentation of my homework 2. And these are contents. First, I'll briefly introduce a background of this homework, and then I'll briefly explain of my problem solving. First, background. And first, resampling methods. Like not only just fitting model through the training data set, by resampling methods, we can obtain new information. Resampling methods includes two methods, like repeatedly drawing samples from training set and repeating a model of interest on its sample. And I'll give you two representative resampling methods, which are cross-validations and bootstrap. And the validation set, first one, before resampling methods, I'll briefly explain about the validation set approach. The validation set approach divides the set of observation in two parts, which are training set and validation set. And the model is fitted on training set, predicting the responses of the validation set. And validation set error rates estimate the test error rate. So we can estimate the test error rate, which is usually not known, but still with simulated data, we can do that. And as you can see the figure below, we can separate observation data into training set and validation set into two parts. And through the validation set approach, we can decide how flexible the model is for the best prediction of the responses. And as you can see in the left figure, we can decide the degree of the polynomial, which means flexibility of model like this, through the estimated MSE curve. And also we can do the validation set approach multiple times with different split of the data set, and then we can derive these like 10 different validation sets like the figure on the right side. But as you can see from these two figures, we can see the drawbacks of the validation set approach. And actually, yeah, as I told you before, we can determine the appropriate flexibility of model, but still on the right side, you can see the results can be very different from the implementation of the validation set. And also we split the data set. Also, the model is trained on the fewer data observations, so the performance could be worse. So that means in other words, then it means like test error rate can be overestimated. And then there is a leave one out cross validation method. And this one is a little bit different from the the validation set approach. Here is a single observation is used for validation set, and rest of the observations is used for training set. So, and then LCV provides approximately unbiased estimate for the test error. And in terms of MSE of this method, MSE for single observation is highly variable. So LCV estimates the test MSE by averaging N, which is number of observations. So it means the validation data, which is single data, is changing to like whole different data. So we can do this like N times, and then we can average. So we can estimate test MSE averaging these test error estimates. So advantage of this method over the prior method is that LLCV's output has less bias due to use almost whole observation for training. And also it doesn't have randomness. And the other method is k-fold cross-validation. Is different from the leave out one's cross-validation. So it's an alternative to LOCV. So for LOCV, the cross validation set was just single data, but here it's just not single data. So k-fold cross validation randomly divides the set of observations into k groups, and one fold is treated as validation set, and the rest remaining folds are training set. You can see here this figure, and yeah, just choose one fold among the k folds, and then as a validation set, and the rest of them is used for training. So this process is repeated k times, alternating the validation set. So we can result in k estimates by doing this k times, as I told you before, and we can estimate we can result in k estimates, and then we can average it, and we can derive the k-fold CV estimate. However, we don't know about the true test date, so it's hard to determine accuracy of this estimate because we don't know whole test data. So obviously, it's hard to know true test MSE. But in the textbook, in the textbook, like they say, like with simulate data, they can just try like true. I mean, they can derive true data, true test MSE, and then we can evaluate the estimate. And like most of the times, actual true test MSE is our interest. So that's why we're doing cross-validation method to estimate her test MSE. But sometimes we are only interested in minimum point of the like MSA curve or cross-validation like MSA curve like that. So as you can see here, the blue lines of the each graph means true MSC. But we can actually, we can estimate this true MSA curve, but sometimes we are only interested in the minimum points. So the cross-validations method it can be used to estimate the minimum minimum like point. Like we can determine like this flexibility can be used for optimal like optimal estimator. So the advantage of k-fold cross validation over LOCV is that it computationally advantageous, and also it gives more accurate estimates than LOCV does. And it can be explained by bias variance trade-off for k-fold. As I told you before, LOCV give approximately unbiased estimates of the test error, but it has a higher variance than k-fold CV. Let's dig into the why. And why is it has higher variance? So LCV is performed averaging the outputs of n fitted models, which are trained on almost identical set of observation. So between a set of observation, the only difference is the single data. And outputs of LCV are highly correlated to each other because of this, and then it tends to have higher variance. In k-fold CV, the overlap between set of observation is less, so that means the outputs are less correlated, and it results in less variance. And the last method is the bootstrap. It's very widely applicable and extremely powerful statistical tool to quantify the uncertainty with a given estimator. Like, for example, we wish to invest a fixed sum of money alpha into two financial assets. There is returns of X and Y. So in terms of investment, we try to minimize the uncertainty, which is variance of the revenue, which is expressed here, alpha X plus 1 minus alpha times Y. So we have to decrease of this variance. And actually we can derive the alpha that minimize the uncertainty like this. However, the quantities like sigma x squared, sigma y squared, and sigma xy are unknown in reality because we don't know whole data of each. So we should use the estimates of these variance to derive estimate of the alpha. And by generating independent simulate data sets, estimates and alpha hat can be calculated many times. So that means we can estimate of the standard error of alpha hat. So we can estimate, that means we can estimate the uncertainty of the revenue, not revenue, but with uncertain, with variance of the alpha. So, but actually, this cannot be applied in practice because as I told you before, it can be applied by generating independent simulated data set, but in reality, we cannot do that. But here, Bootstrap allow us to estimate standard error alpha hat of alpha hat by repeatedly sampling observation from the only original data set. So we can do this same process only with what we have. And then the sampling is performed with replacements, and by doing that, we can get B different Bootstrap datasets, G1, G2, GB, and with these datasets, we can get the estimates of alpha, and then we can obviously calculate of the alpha hat's standard error, which means uncertainty. And the figure below, just left sides, shows the alpha's graph, alpha's distribution calculated by independent set of the observations, and then the middle one is derived by the bootstrap. So as you can see, these graphs are very similar to each other. So that means we can use the bootstrap to quantify the uncertainty of the estimator. So, and then from now, I'll give you explanation of my problem solving. So I chose problem number 4, and I'll start. First, first problem is to fit a logistic regression model that use income and balance to predict default. So first I loaded data like this, and then they don't use the student data for the prediction for the, so I just dropped the student and default for input, and we set input and output like that, and then we fitted data of the using logistic regression, and the results are shown in the right side. And then problem B, first process split the sample set into a training set and validation set. So I just did that by using train test split function. And then the second one with a multiple logistic regression model using only training observations. So with the training observations, I also fit multiple logistic regression model with the same way that I used for first problem, and the results are shown on the right side. And then I have to obtain the prediction of the default status. So with the fitted model, I just use the predict method of the fitted model, and then with the validation observations, and then I just sorted the results of depending on the range of the 0.5 greater than 0.5, which means it's default. So so yeah, by doing that, I got to label the results like that. So if it's default, then it's true, and if it's not, it's false. And then I have to compute the validation set error. So yeah, this Y valid data is just original data, and then I just compared, like labeled prediction, which I did in the last problem, and then I compared, and if it's same, then it's gonna be false, and if it's not same, it's gonna be true, and then it's gonna the NP sum is gonna calculate count the number of truth because which means the validation error. So yeah, we can derive here like 145 validation error rate. And then I just did this problem by repeating problem B 3 times. Yeah, I just use random state like the 1, 2, 3. And then with the for structure, I just repeat it 3 times. So, and then I just got the results. And yeah, the validation set error rate are quite similar to each other in each implementation. And then last problem is that I have to consider logistic regression model that predicts the model probability of default using income balance and dummy variables for students. Estimate the test error for this model using the validation set approach. Comment on whether or not including a dummy variable for students leads to a reduction in the test error rate. So the only difference is that I didn't drop the student data for the prediction, and I fitted more than 9, and I did 3 times with the different random state. And I got the results like this. And actually validation set error rates are higher than when I didn't use the standard student data. And also, as you can see in the I would say it's the p-value of the income, which is quite high. So that means um, maybe it's not helpful for us to just use the student data. And also G value is quite small. The absolute value of the G is quite small, and then also the p-value is quite high. So that means we don't have to use the student data for the prediction. And this is my presentation, and thanks for listening.